I'm going to leave it like this. The writer from example 1 and example 2. Remember that guy? Yeah. That guy he loved that Ferris wheel. He leaves the fair. Okay, the fair's over. He goes home, and what does he do? What a nerd. He constructs a perpetual motion machine shown at the right. So here's what he built. Okay. It is a weight attached to the end of a long spring that's bouncing up and down. As it bounces, its distance from the floor, so we're measuring its height above the ground, varies sinusoidally with time. The writer sets the spring in motion by compressing it to a high point 60 meters above the floor. Hello, welcome. At which time he starts his stopwatch. You can sit wherever you want. Right here. You can sit right here today. So he's holding it up to its high point, compressing the spring with one hand, and he's got his stopwatch over here. Siri, start, and he lets go. Okay, and the stopwatch starts. At which time? Okay, so 1.8 seconds later, it gets to its closest to the floor, which is 40 centimeters above it. That's kind of slow, right? He lets it go in like 1.8 seconds. It's all the way down. That's a slow oscillating spring. Part A, sketch the graph of this sinusoidal function. Now, the picture over here is pretty helpful. Hopefully, you can see the numbers here. But if not, you can get them from the description. When it's at its high point above ground at 60, the closest it gets to the ground of 40. So you can kind of see that it's going to oscillate above and below that right there. Now, it's a perpetual motion machine, which means this guy went home, and, of course, he neglected air resistance and gravity. Okay, so this is a special room in the house, no doubt. When it says to graph it, is the little sketch that I drew right there good enough? No, it's not. We have to do something much more detailed. Okay, so we know it goes up to 60. We know it goes up to 40. So here we go. What are we measuring on the y-axis? Height. Good. The height above the ground. So I'm going to call it h of t, and we're measuring it in what? Centimeters. Great. Centimeters, naturally, in America. Centimeters. And, of course, we're measuring time on the x-axis, and we're measuring it in what? Seconds. Good. So that's step one. What are your units? In the Norman problem, there was one on the worksheet where you were measuring Norman's distance, the rock distance above ground, as a function of the distance traveled down the road. And then the one I gave you on Friday, you're measuring it against time, which is a little bit more interesting. Okay, so let's go ahead and mark the vertical axis first, which I think is a little bit easier. The highest it gets above ground was what? 60. Let me put that on the other side here. And the lowest it got was 40. So I'm going to do something like that, and then you could put like a little break in your graph right there if you want. Have you ever seen that before, the little line? That just means that, of course, we know it's not the scale from 0 to 40 as it is from 40 to 60. So it's like we're breaking the y-axis and moving it down because all that extra space is not needed. You don't even have to really show that. Now, what else could I get here once I know the high and low point? The sinusoidal axis, because in relation to the high and low point, it should be where? In der Mitte, right? Which is German for what? In the middle. Yeah, good. What's the value that's halfway between 40 and 60? 50. Now, it could be intuitive, or to get the average of two numbers, you just add them and divide by 2. So you add them, you get 100, divided by 2, you get 50. So 50 is the sinusoidal axis, which means in our equation, it's going to be what letter? D. A. D. A. D. 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 Yeah, now speaking of A is going to be the distance from the sinusoidal axis to either the high or the low, which is 10. Right, from 50 to 60 or 50 to 40 is 10 in either direction. So there's the vertical axis. You can kind of collect your vertical information off to the side for the equation. And now for the t-axis. This is the one that's always a little bit more fun. This is what we get up in the morning for. He's starting it by compressing it to a high point. So t equals 0 is also known as the y-axis. So this problem starts off pretty nice because he's starting it by compressing it all the way to a high point. So there's really no awkward phase shift here. Now there's some information here. It says 1.8 seconds later, it gets its closest to the floor. So if I just want to come out here and just draw that as 1.8, just kind of arbitrarily from the y-axis, not too far away, not too close. I know it's at its low point for the first time. That's really all we need to finish the rest of the graph, right? Because from a high point to a low point is what fraction of a cycle? A half, okay? So if I kind of bisect that, what's half of 1.8? 0.9. That 0.9 right there is perhaps the most important time value because that is your quarter cycle interval, which means that's where it should be on the axis. Now that you've done that, notice the spacing on your graph. The distance from the y-axis, which was at a high point, to the axis point now, which is 0.9, that distance is what you want to preserve. So on your graph, you're going to go ahead and just put down critical values that are eyeballed about the same distance away. And then you go through and you number them, right? And you just count by what each time? 0.9, 0.9. So 1.8 plus 0.9 is 2.7, then 3.6, then 4.5. Look what's happening. The ones place is getting one bigger, and the 10th place is getting one smaller. I see the pattern. Just factors of 9. 5.4, 6.3, 7.2, 8.1. We could keep going, but that's as far as my graph extended. And now we put the rest of the values. So there's low, 2.7 will be back on the axis. 3.6 is high. 3.6 is pretty important because it's the what? It returned to the high point for the first time. That would be it's a full cycle, so it's the period. The period, remember, is the smallest value of time in this case for which the graph repeats itself, which would be 3.6. So then we go back down to 4.5, then to 5.4 at a low, 6.3, and 7.2 coming up. So with our critical values there, we then just connect the critical values with these exaggerated curves, curving up, and curving down, concave down. We turn the corner to show that it keeps going. Do I want to show a point to the left here? Yeah, I could show it for graphing purposes, but in terms of the relevant domain, our relevant domain here is what? What values of t make sense? 0 to its perpetual motion, right? So to infinity, right? Long after the rider has perished, this thing should keep going in that special room where both wind resistance and gravity are neglected. Special room. Okay, so part A, we're done with part A. Part B, find a particular equation. All right, so I named my function on the y-axis what? H of t. So give your function a name. The amplitude comes first, which is 10, and you have the option of making it plus or minus. If we want to write the easiest equation, that is without a phase shift, could we do it? Yes, and it would be a what? If we're starting at t equals 0, good, at a high point, remember chala starts at a high point. So you could do it with a positive cosine and no phase shift. So positive cosine, parentheses. Does the period go next, 3.6? No. What goes next? The b value, which is 2 pi over 3.6. Now let's see how we can contend with that. Does 2 pi over 3.6 simplify? It sure do. It's 1 pi over half of 3.6, which is 1.8. Now here's what I can promise you. If I ask you for the equation of this on a multiple choice, that b value would not be there because you have mixed notation. You have a fraction and a decimal, both of which are used to communicate parts and numbers. Yeah. Yeah, watch this. The period is equal to 2 pi over b. So if you want to solve that for b, multiply both sides by b. You get bp, not the oil spill people, but b times the period. And then if you solve for b, you get 2 pi over p. So it's an equation that works both ways. They kind of just interchange. We get the period, remember, from the graph, and we convert it to the b value for the equation. If we start with the equation, we get the b value from the equation, we convert it to the period so that we can sketch the graph. Now let's see what I would do with this. 1.8 is a decimal. Let's go ahead and write it as a fraction. I got to do that down here. 1.8, how would you read that properly instead of 1.8? 1 and 8/10, which is the same as 1 and 4/5. If you convert that to a rational number, you get 5 plus 4 is 9. fifths, right? So there's another version of 1.8. So let's go ahead and write 1.8 as 9 fifths. Now we have a complex fraction. So dividing by 9 fifths is the same as multiplying by its reciprocal, and I get 5 pi ninths. That is a much more seductive value of B. 5 pi ninths. That's what I would put for the B value. So just a little bit extra work for you, right, which is still fun. Now, because there's no phase shift, we don't need to put an extra set of parentheses and do plus or minus. We're starting at a high point, so make sure you put your independent variable, which is t naught x. And are we done? No. If we were just measuring the relative distance of the weight above and below its resting position would be the sinusoidal axis. That would be the equation. Because we're measuring it above ground, we got to shift it up 50 units, which is your D value. Now, of course, from here, you could write any other equation if you want. And what would be the horizontal shift if I wanted to use a negative sign? Where on the graph do we have a negative sign? Negative sign would start on the axis, right? Sign always starts on an axis. But instead of going high, for a negative sign, we'd be going low. So it would be at 0.9. So you'd have t minus 0.9 or t minus 4.5, either one. If you wanted to start here at 1.8, it would be a what equation? Negative cosine. So I don't care on the free response which equation you write, as long as it's correct. I will look at your equation, and I will look at your graph, and if they match and it gives it, you're good. It just so happens that a positive cosine is the easiest one because there is no phase shift. Okay, now that we have the equation, what are we going to do? Well, we're going to answer questions. What is the distance from the floor when the stopwatch reads 10.5 seconds? At this time, is the weight moving up or down? So at 10.5 seconds, is that a t value or an h value? T. So what you'd have to show me on the test is h of 10.5. And there's no converting because we're measuring time in seconds. So once you put h of 10.5 equals, I'm going to go to the calculator now. And here's probably the most important thing. You've spent all your time so far getting your graph in a beautiful window on your paper/iPad. Graph it, your equation, in your calculator in the same window, and you should see the same graph, right? If you don't, something's wrong. All right, so let's type in our equation, which was 10 cosine. Parentheses is automatically open. If you want to use the alpha y equals, that gives you n over d. That's a nice way to type in 5 pi ninths. And then off to the side, x, of course, instead of t, close parentheses, plus 50. Now, here's one thing that you should automatically check. What mode should we be in? Radian. So before I hit graph, I'm going to check the mode. I am in radian mode. That's good. If you're in degree mode, all your numbers are going to be off. Yeah, let's go to the window. The window is now going to be easy because of what we've already done. We are graphing it from x equals or t equals 0 to, mine went out to 7.2. So I'm going to set my x min to 0, my x max to 7.2. And for your scale, you can always leave it at 0. But if you want, you can set it to your quarter cycle counting interval, which was what for us? 0.9. That would allow you to see the critical values at a mark, but you can leave it at 0. Now your y min, let's go to our graph. We are way above the x-axis. So I like to put like -5 so I can see the x-axis and go a little bit above 60. So I'm going to go like from -5 to 80. That gives me a little bit of a buffer. -5 to 80. Because the calculator uses the top and the bottom of the screen to write information, and you don't want it to interfere with your graph. And for your y scale, I'm just going to leave it at 0. The rest of the stuff you can always leave as default, okay? That's all we need. So there's your window. If you hit graph, you should now see something that resembles, again, what you have on your paper. And if it doesn't match, something's wrong. A lot of people were having a hard time with the Norman problem on Friday because you were graphing it in a window from like 0 to 10, which interestingly gave you a perfect sinusoid. But 10 seconds when the wheel is spinning that fast, That's way out there. So you really needed to graph it like from 0 to like 1 second, and then you would see 10 cycles. So always good to like sketch at least 1 or 2 cycles on paper, and then set your calculator window to match. Does this look like the one we graphed? Yeah, looks good. You can even verify a few points. Watch this. If you hit the trace button, punch in a 0, hit enter, you get 60. Is that where we started? Yeah, let's type in one more to verify. I know that at 1.8, I'm supposed to be at a low point. See that? Let's see if the calculator knows that. If I just type in 1.8 or trace 1.8, it gives me a low point of 40. What do I know now? I know that my equation and my graph are spot on correct. And so now I know I'm going to get the correct answers when I use the calculator. So here we go, h of 10.5. There are 2 ways to do it. Number 1, if your window on your graph goes from 0 to at least 10.5, which mine doesn't, you can use your calculator. Well, no problem. If you want to include 10.5, just change your x max to 11. Then you got to wait for it to graph again. But at least it's fun if you imagine like you're riding on the spring. Or not. Don't make sounds like that during the test. Now you could just hit the trace button, type in 10.5, and watch this. Hit enter. Ding, 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 ding. There you are. And how many decimals do we report? There's the y value. 3. So 58.66. Do we need that last 0? We sure do. So on your paper, 58.660. And what units would it be? Centimeters. Okay, now we're going to answer the question. At t equals 10.5 seconds, comma, the weight is 58.660 centimeters above ground. We're interpreting that as a vector now. It's positive, so it's above ground. Moving, we can say that, moving, what, up or down? Well, if you do it on the graphing screen, you can actually see that it's on its way what? Up. So that's the benefit of doing it from the graphing screen, moving up. But on the Norman problem from Friday, it happened way down the road. And I think Jenna asked how you would do that. You could either set your window to something way down the road. You could set your x min and x max just to something that includes that time value. I'll show you what I mean. Let's say it's a perpetual motion machine, right? So let's say I want to know where is it at 1,526.2 seconds. I'll take the seconds out of there. You don't want to have to sketch your window to go from 0 to whatever, because what's going to happen? It's going to start having so many different cycles. So what you can do, if you want to do it from your graphing screen, is set your x min to something like 1526, and then your x max to like 1527. And then 1526.2 is somewhere in there. Now you're just going to see a little piece of the graph, but it's way down the line. There you go. And now you can hit the trace button and type in 1526.2, and there you go, 59.396 or 397, and you can see that at that point it's traveling what? Up. So that's one way to do it. Certainly works great, but you have to adjust your window. The other way to do it, I told y'all, is from the home screen. So let's review that. Returning to the original problem, I wanted to know where it was at 10.5. So in general, since I have my equation in y1, alpha traced, remember, is your shortcut to all your y's. I have mine in y1. Open parentheses, 10.5, close parentheses, that's function notation. Boom, there you go, 58.660. If you think you need to use that again, hit stow alpha A. And there it is with all the decimals stored, if you think you might need it. Now, is it going up or down? I don't know. Let's come back up here. Recall that. But now before I hit enter, I'm just going to add like 0.001. I'm just going to add a smidgen of a second. That's like 1/10,000th of a second later. Compare it. 660 it was before, now it's 661. So later in time, it's actually moving what? Up. That's another way to do it. The smaller you can make your time interval, the better likelihood that you haven't turned the corner and already come back down. And then in the Norman problem, you needed to go out several zeros because it's rotating so quickly. So I don't care how you do it. Just remember you can adjust your graphing window and get a nice visual. Okay. Part C. Oh, no, Part D. What is the first positive value of time when the weight is 47 above the floor? So the other type of problem is I can give you the y value. So now you would say h of t equals 47. That's what you would show me on your paper. And now I know the equation you're solving. So how would we do that? Well, from the graphing screen, we would type in 47. Now here's the bad thing about adjusting your window to answer a question. You got to go back to an original window, which would be like from 0 to, I'm going to go to 10 seconds or 12 seconds, and wait for it to graph again. Which again, if you imagine you're on the spring, you're going for a ride, it's free, it's safe. The clock is ticking though, and second period awaits you. All right, there it is. So now we have a visual of where it's equal to 47 above ground. So we just need to read carefully. We want to know when it's 47 for the first time. It doesn't matter if it's going up or down. So there's the first time it's 47 going down. What if I said for the first time going up? Would you want this first point of intersection? No, you would go to this one here. So it's important to know which one you're looking for. Second trace then, number what? 5. And again, this is the easy part. Is this your first curve? Hit enter. Yep. Is this your second curve? Sure, calculator. Hit enter. Now for your guess, you can scroll on the second curve, which is the straight line. It's a little bit faster. And then get over to where you think it is and hit enter. And we get 1.074. Now another heads up. When you go back to your home screen, if you hit X enter, boom, there it is. It has currently stored it as 0.074. If you think you need to use that again, store it as maybe alpha B. I don't know if you're going to use it again, but if you think you might need it, store it. Now, what would you write on your paper? This is where people kind of get the notation mixed up. You put h of t equals 47, and then underneath there you put t equals 1.074 or 075 seconds. This is a check. You're showing me the equation you're solving. Here's your numeric answer with 3 decimals and units. No sentence in this case, yeah. I would ask you in the instructions to explain the meaning of your answer. I would in a sentence. All right, and then part E, the first part E. Notice there's 2 part E's. It's always good to have a double party, right? During the first 9 seconds, for how long is the weight at least 53 centimeters above the floor? All right, so what am I going to show? At least 53 means it could be 53 or greater or 53 or smaller. 53 or greater. So I want to know for what values of t is h of t greater than 53, yeah? How am I going to solve that during the first 9 seconds? Well, the first thing I'm going to do is I'm going to go to y equals, and I'm going to graph 53 for my y value. And then I'm going to go to my window, and I'm looking for the first 9 seconds. So I'm only going to graph it from 0 to 9. I don't want to be distracted by other values. Hit graph. Watch it graph again. Imagine you're riding the spring. It gets kind of boring, kind of like the Ferris wheel. Oh, yeah, there it goes. Yep. Okay, now here's the cool part. Notice that there are 2 complete symmetrical intervals where it's above. And then this one here, this happens to be a half cycle because we started at a high point. But this isn't necessarily going to be a half cycle on the test. So here's what I'm going to do. I'm going to find this point of intersection and this one, or this one and this one. And to find the distance between them, what am I going to do? Subtract them, okay? So let's do that first. Second trace, number 5, enter, enter. Now, because I'm close to this one here, I'm going to use the first one. But it doesn't matter which ones you use. So I'm going to find the left endpoint first, enter, and I get 2.874. This is where you have to use the calculator. If you go second mode, quit, and you hit X, there's 2.87. Now, that's the value that we need to use. So I'm going to write that down. That's T equaling 2.87 or 2.874 seconds, and I'm going to store that as A. So this is the first time I actually need to store value. So I'm going to call it A on my paper. On my calculator, I'm going to hit stow alpha A, and there it is. And what do we do next? Well, we find the next point of intersection. Same thing, second trace number 5, enter, enter, come on in, and we scroll over, and we hit enter, and we get a nice visual that it found the 101, 4.325. Get back to the home screen. Notice if you hit X again, it has overridden the previous value of X. Good thing we stored it as A. And I'm going to store this one as alpha B. And I will write that on my paper as well. I do want to see the values you're using. So T equals 4.325 seconds, and we'll store that as B. Now there's one last value that we need to find. The value where it intersects right here is starting at 0, so I need to add that to it. And it's not always going to be a half a cycle. So let's go ahead and find it. Second trace number 5, enter, enter. And then we'll scroll over to that one. Come on, get there, get there, get there, get there, get there. There we are. Hit enter. And we get 0.725. So one last time, go to the home screen, second mode. You hit X, enter, you see it. I like to see it before I save it. So once I hit X, enter, then I just hit stow as alpha. What comes next in my storing letters? Alpha C. Hit enter. On my paper, I need to show that. T equals 0.725 seconds equals C. And now I'll show what I'm doing with those values. So total time, some kind of transition. So total time above 57 centimeters is, now to find the distance from A to B, it's going to be B minus A. And how many of those did I have? I had one of them here. I had another one there. So I need to double that. So that's 2 of those. So 2 times B minus A, and then plus what? Plus C, that little time from 0 to C. That communicates what you're doing. Now all you have to do on your calculator, it's kind of fun, using your calculator as a tool. You just type that in. 2 parentheses alpha B minus alpha A, close parentheses, plus alpha C, hit enter. And now you report your final answer to 3 decimals, and it should have no rounding error because you've been using stored values. So we'll report it now in the end to 3 decimals. And what are the units? Centimeters? Seconds. There you go. So for a problem like that, if it's a full cycle of an intersection, it didn't matter if you use the first set of intersections or the second. But then make sure you're adding back any little piece that's either from the front or on the back end. I love that type of problem. That's using your calculator as a tool, like I said. If you are off in the 3rd decimal place, notice that it's 3.6271. So the only correct answer I would take is 3.627. If you're off, if you have 3.628 or 3.626, you would not get it correct. But I would still give you a check for this right here if I see what those values are, because that's communicating your method, and then your answer would be a separate check. Okay? So that's why the free response is so important, to show me how you do it, not just what you did or what your answer is. All right, and then the second party that we're attending, party, if the writer's little sister, oh, that's cute, starting the machine, oh, that should be what? Started. He hired her. He needs to hire a better editor, too. If the writer's little sister started the machine when the writer was at the yogurt shop, and then the writer came home and happened upon the machine already in motion, uh-oh, it's gone. I wasn't here when it started. And now he starts his stopwatch when the weight is 51 centimeters above the floor and moving away from it. what would the new equation be? So imagine that he comes in and he sees this thing going down and up and 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 down and up. And he happens to just walk in when it's at 51, which would be right about here, and moving away from the floor, which would be, in this case, what? Moving up. So right there. And it doesn't matter if it's like past zero. The equation, because of the periodicity of this function, all I need to do is figure out what that time value is, and I can shift my graph over to the left or right. Well, let's see. We'll figure that out. I want to know now where h of t equals 51. So that's what I'm going to write on my paper. And one more time, we're going to go to y equals, and instead of 53, we're going to change it to 51, and we get to watch it all graph all over again. We are having a blast. We are experiencing leap day to its finest. All right, which point of intersection do we want? The first, second, third, fourth, or fifth? The second one. So second trace, number 5, or 5. And then we scroll back here, nach links, to the left, and we hit enter, and we get 2.757. So again, on your paper, you're going to have t equals 2.757 seconds. And so the equation now, if we take the old equation, which was this right here, I'm just going to lasso it with scissors, which I always love to do, just like the Cowboys did back in the day. I'm just going to modify this and shift my graph over by that amount. Now the question is, if I want this, which was 2.757, which makes perfect sense on my graph, I want that to be the new y-axis. Do I need to shift my graph to the left or to the right to make that point there the new y-axis? To the left. I need to take that graph and move it to the left. So to move it to the left, is it going to be a plus or a minus in your equation? Plus. Good. And you can go 2.757. No, it's the exact same graph that I had. So the only thing I'm doing is I'm modifying my existing equation that I already had written by some shift. Now, if you're not sure if it's right, you could come up here and watch this. You can actually modify it. 5 pi 9ths, click parentheses, and you can hit plus 2.757. I did miss it. Close, close, plus 50. And when you graph it, it should look exactly, oh, I missed the X. Okay. Anyway, you could sketch that graph and make sure that it's actually the graph you want. And if you shifted it the wrong way, you'll be able to catch your error. Notice this starts now at 57, moving upward. All right, so there we took the whole class to do one problem. Any problem like that or the Norman problem, your free response on Wednesday. Tomorrow we'll finish the notes. Remember, the bonus is due tomorrow. Shared Google Drive folder. It's totally optional. The worksheet for 5.5 is due on Wednesday. If you are not here on Friday, your Norman problem, which I have a copy of up here, is also due on Wednesday. All right, that's it.